Alright, so this is lecture 9, method of characteristic, and the focus is on something called distinct roots. I will explain why this is just the focus for the lecture. So the learning objective is that hopefully at the end of this lecture you could be able to know how to identify characteristic equations, or more specifically characteristic polynomial equation from a linear constant coefficients ordinary differential equations. And you could be to use that characteristic equations to solve the real distinct roots, and from there get the solutions of the differential equations. All right, so this method particularly can be used to solve for the second order homogeneous linear differential equation with constant coefficients. So that is a very specific setup for the second order differential equations. So you see this definition already in the last lecture that we want to consider the second order differential equations of this form. But we make further assumptions that P of t, Q of t, and R of t are constant, and the right-hand side of the differential equation is equal to 0. Therefore, again, you have the homogeneous linear second-order differential equation with constant coefficients. And more specifically, we're going to focus on this type of equations. All right, where A, B, and C are just some arbitrary constant. Of course, it depends on the formula, depends on the problem that you're working with, and you have different value for A, B, and C. So we seek the exponential solution of the form y equal to e to the rt, and r is the parameters that will be defined later for the differential equations a times y double prime plus by prime plus cy equal to 0. You may wonder, where is y equal to e to the rt coming from? Is actually from the idea of this first order differential equations, right? If you don't have the second order term, so that means you don't have this term. Let's assume that you don't have this term, then it will come down to be just the first order differential equations. That is, this equations can have by prime plus cy equal to 0. This is the first order differential equation, is linear, is homogeneous with constant coefficients. Then you can use separations of variable to solve this particular equations. And you get y prime equal to negative c over b times y, or you can just use some capital A times y. So this is y prime equal to a times y. It looks like an exponential growth model, or it's an exponential decay model. That means that the solutions of this equation are going to give you an exponential functions. From that idea, we're going to follow through with that when we add another term into the equations, and that extra term is the second order. And that's why it's kind of give you a suggestions. In a way, you can assume that at this level, a guesswork, but is a very educated guesswork, right, from what we have known so far. So that's why we assume to have, let's try an exponential solution of the form y equal to e to the rt. And depends on the value of r, we will have different scenarios. Okay, but e to the rt is a trial solutions, and there's a very special thing about exponential functions. That is, when you take the derivative, e to the t kind of stay the same for the first derivative, second derivative, or any derivative for that matter. And you will see how nice that could be, because you could be able to go from the second order differential equations down to a quadratic equations. And hopefully at this level, you can recognize quadratic equations and use the quadratic formula to find the solutions of quadratic equations. Okay, so again, the trial solutions here is y equal to e to the rt. So y equal to e to the rt, and y prime is equal to r times e to the rt, and y double prime is equal to r squared e to the rt. Then you substitute this into the differential equations. Substitute the derivatives into the differential equations. We get that a times y double prime, that is r squared e to the rt, plus b times y prime, that is br times e to the rt, plus cy, that is c times e to the rt equal to 0. Now, e to the rt can be a common factor, right? So you take e to the rt as a common factor, and then divide both sides for e to the rt, because e to the rt is different from 0. Okay, therefore you left with just a r squared plus BR plus C equal to 0. So as I mentioned earlier, the very nice thing about this trial solution is that it helps you to transform a second order differential equations to the second order polynomial equation, or in this case, the quadratic equations. Okay, and you can use the quadratic formula to find the solutions of these equations. And these equations, for in the context of differential equation, is called the characteristic equations. So there's two names that you can use interchangeably. The first one is the characteristic equations, and the second one is auxiliary equations. So auxiliary equation meaning that is not the original differential equations, but is a companion algebraic equations, right? That is, you turn from the original differential equations to something else that you can work with to help you find the solutions of the original differential equations. It also has the name characteristic equation because the root or the solutions that you're going to find in this quadratic equations kind of characterize the behavior of the solutions. Right? It's later carried meaning can help you determine if the solution is going to be growing, or the solutions will be decay, or the solution oscillate in the system. Okay, so two names, you can use them interchangeably, doesn't matter which one. But this is quadratic equations, therefore you can find the solution or the root of the quadratic equation using the quadratic formula. Okay. The root of the characteristic equations can be found using the following quadratic formula. So r equal to negative b plus n minus square root of b squared minus 4ac altogether divided by 2a. Right. And of course, as again at this level, hopefully you recognize this formula, and there are three different cases depends on the value of b squared minus 4ac. Right. When b squared minus 4ac is positive, then you will obtain the two distinct root roots. Two distinct root roots, r1 and r2. Right. So from here, from the distinct root roots, you lead you to the solution of the differential equation. So remember, the trial solution is of the form y equal to e to the rt. In this case, r equal to r1 or r equal to r2. So you got two solutions to the differential equations. The solutions are of the differential equations are y1 equal to e to the r1t and y2 equal to e to the r2t. In addition, as we talked about this in the last lecture, the linear combinations of these two solutions or these two functions is also a solution to the differential equations. In addition, the general solution of the differential equation is you have y equal to c1 times y1 plus c2 times y2, or c1 times e to the r1t plus c2 times e to the r2t. This general solution or this function is also a solution to differential equations. Right. So that's the first case. Now for the second case where b squared minus 4ac is equal to 0, then you have a repeated root. So in this case, r is equal to r1 equal to r2. The solutions are r1 equal to e to the rt, and so this is y1 equal to e to the rt, and y2 equal to t times e to the rt. So repeated root is r equal to r1 equal to r2, so hopefully you recognize that. But the solution, so for the first solution is understandable because it's coming from the solution trial, the trial solutions. However, what about the second solution? So I will show you how to get the second solution for the case of the repeated root in another lecture, because you need to use another method called reductions of order in order to obtain the second solutions. But in this case, I'm just going to show you the solutions in theory. But in practice, I'm going to show you how to get the second solution from the first solutions. Okay. The general solution is so the general solution is the linear combinations of these two solutions. So y is equal to c1 y1 plus c2 y2, or this is c1 times e to the rt plus c2 times t times e to the rt. Again, the second solutions here can be solved or can be obtained from the first solution. And again, I will show that in another lecture called reduction of order. Now for the last case where b squared minus 4ac less than 0, you have complex roots. And the solution of complex root will be also derived in another lecture, but I want to give you the formula here in this lecture. Just the formula. Where they are coming from, I will show you later. So the solutions are y1 equal to e to the lambda t times cosine of mu t, and y2 equal to e to the lambda t times psi of mu t. So these two solutions you have seen in one of the examples in the last lecture, lecture 8, where you have to find the Wronskian of these two functions, right? So if you go back to lecture 8, you will see this is the two functions we are talking about. Right? So the two functions actually coming from the case of complex root for the characteristic equation. And therefore the general solutions is y equal to c1 y1 plus c2 y2, or this is c1 times e to the lambda t times cosine of mu t plus c2 times e to the lambda t times psi of mu t. So those are the three cases for the characteristic equations. From the characteristic equation, you can find the roots, and from the roots, you can get the solutions to differential equations. And today, in this lecture, we're just going to focus on the case of two distinct roots. In the next lecture, I will talk about complex root and after the test. That's after the test. And in lecture 10, we have the complex root. In lecture 11, we're going to have reduction of order to derive the solutions of the repeated root. Okay. Now I'm going to move on to some examples here. In example 1, I have the initial value problems. That is the differential equation in two initial conditions. So the differential equation is y double prime plus 5y prime plus 6y equal to 0. And the initial conditions are y of 0 equal to 2 and y prime of 0 is equal to 3. I'm not going to be too strict on the derivations of the second order differential equations to the characteristic equations. But if you don't know right away how to write the characteristic equations, you can follow these derivations right here. That is, you start with the trial solutions, y equal to e to the rt, find the first derivative, second derivative, substitute into differential equations, and get the characteristic equations. But hopefully is clear that you have a stay the same, y double prime becomes r squared, b stay the same, y prime becomes just r, and c stay the same, and y that is the zero derivative, so you don't write that down in the characteristic equations. So from this differential equation, the characteristic equation is you have r squared, that is from y double prime, plus 5r, that is from y prime, plus 6 equal to 0. And from here, you can factor the quadratic equations, and you get that r plus 2 times r plus 3 equal to 0. Okay. And you obtain two solutions. So this is the case of two distinct roots. You have r1 equal to negative 2 and r2 is equal to negative 3, or vice versa. Then you have r1 equal to negative 2 and R2 is equal to -3, the solutions to the differential equation are y1 equal to e to the negative t, and y2 is equal to e to the negative 3t. So I just write down the solutions of the differential equation, but the request is, can you find the general solutions of the differential equations? So to write down the general solutions of the differential equation from the two solutions y1 and y2, the general solution is the linear combinations of y1 and y2. But technically, before writing down the general solutions, you should find the Wronskian of y1 and y2, and then write the general solutions. Okay. So when you calculate the Wronskian, you have to make sure that the Wronskian is different from 0. So the Wronskian of these two solutions is, so W of y1 comma y2 is equal to the determinant of y1, y2, y1 prime, y2 prime, and is equal to, so y1 is equal to e to the negative 2t, y2 is e to the negative 3t, y1 prime is negative 2 times e to the negative 2t, and y2 prime is negative 3 times e to the negative 3t. Use the formula to calculate this 2 by 2 determinants, and you get negative 3 e to the negative 2t times e to the negative 3t minus negative 2 e to the negative 2t times e to the negative 3t. Okay. You combine like terms, right? So negative 3 times e2, so combine the exponent together because you have the same base, is e to the negative 5t plus 2 times e to the negative 5t, or this is negative e to the negative 5t, which is different from 0. So this indicates that y1 and y2 are linearly independent and they form a fundamental set of solutions. And therefore, from here you can write the general solutions to the differential equations. Thus, the general solutions is, you have y of t is equal to c1 times e to the negative 2t plus c2 e to the negative 3t. And that is the general solution where c1 and c2 are arbitrary constant. And depends on the initial conditions, you will have different value for c1 and c2. Of course, depends on the problem as well. And that's what we're going to do for the next part, where you utilize initial conditions, in this case y0 equal to 2 and y prime of 0 is equal to 3, to find the particular solutions of the initial value problem. Okay, that is, you're going to find c1 and c2. So given, so in this case y of 0 is equal to 2 and y prime of 0 equal to 3, we get that. So y of 0 is c1 times e to the 0 plus c2 times e to the 0, or c1 plus c2 equal to 2. So you have one equation. Now the second equations will come from the derivative. So you take the derivative of this function. So y prime of t is equal to negative 2 c1 e to the negative 2t minus 3 times c2 e to the negative 3t. And y prime of 0 give you negative 2 times c1 times e to the 0 minus 3c2 times e to the 0. This is equal to negative 2c1 minus 3c2 equal to 3. So you have two unknowns, c1 and c2, and two unknowns require two equations here in this case. So c1 plus c2 equal to 2, so that's one equation. And then another equation is negative 2c1 minus 3c2 equal to 3. And from here you can solve for a system of two equations with two unknowns to find c1 and c2. So I'm going to combine together these two equations. Then you have that c1 plus c2 equal to 2 and negative 2c1 minus 3c2 equal to 3. So hopefully you know how to solve the system of linear equations here. So the two equations we got is here. Now you can either use substitutions method or elimination method to get C1 and C2 that way. Or if you know linear algebra, you can turn this into a matrix vector form and find the inverse of the coefficient matrix and find the solution of C1 and C2 that way as well. But in here, I'm just going to use elimination method to find the solutions of C1 and C2. Okay, so how could you find the eliminations? How could you do elimination method? So I'm gonna eliminate one of the parameter or one of the values. Sorry, one of the constant here. I'm going to eliminate one of the c's here. So I'm gonna choose C1 to work with. So I'm gonna multiply the first equation by 2. That is 2C1 plus 2C2 equal to 4. Then negative 2C1 minus 3C2 equal to 3. So the second equation remains the same. Now if you add these two equations together, you're going to get 2C2 minus 3C2 equal to 1. That's going to give me negative C2 equal to 1 or C2 equal to negative 1. Then you back substitute this into one of the original equations. So I'm going to plug that in, C2 equal to negative 1 into the first equations. So from here, you got C1 minus 1 equal to 2, or C1 is equal to 3. So you know the value of C1, you know the value of C2, you can write down the particular solutions to the differential equations. So the particular solution is you have y equal to 3 times e to the negative 2t minus e to the negative 3t. And that's how you solve for the solutions of the second order differential equation using the characteristic method or method of characteristic. Okay. Now we're going to do the same thing for the second example. So similar to the first example, in this case you have initial value problem where the differential equation is 4 times y double prime minus 8 times y prime plus 3 times y of 0 is equal to 2, y prime of 0 is equal to 1/2. Okay, so the first thing first is to write the differential equations as a characteristic equations. Okay, so the characteristic equation is you have 4r squared minus 8r plus 3 equal to 0. Again, this, if you don't recognize a factor form of this quadratic equations right away, you can use the quadratic formula to get the solutions or to get the root. Or if you recognize the factor form, then you can go do that as well. So here I have the factor form of 2r minus 1 times 2r minus 3 equal to 0. So the root of the equations is r equal to 1/2 and r equal to 3/2. Then the solutions to the differential equations are, so the solutions to the differential equations are, you have y1 equal to e to the 1/2 t and y2 is equal to e to the 3/2 t. But the request is, can you find the general solutions to the differential equations? Okay, and to find these general solutions, you need to check that the Wronskian of these two functions are in fact different from 0. If they are different from 0, then y1 and y2 are linearly independent, and they form a fundamental set of solutions. So the Wronskian of y1 and y2 is, so here the determinant of y1, y2, y1 prime, y2 prime. This is equal to, y1 is equal to e to the 1/2 t, y2 is equal to e to the 3/2 t, y1 prime is 1/2 times e to the 1/2 t, and y2 prime is 3/2 times e to the 3/2 t. And if you do the calculations correctly, you should get 3/2 e to the t, e to the 2t, minus 1/2 e to the 2t. And then combined like terms, you're going to have e to the 2t as the answer, and that is different from 0. This illustrates that the two functions are linearly independent and they form a fundamental set of solutions. Therefore, you can write the general solutions to differential equations. So the general solutions to the differential equations is you have y of t equal to c1 times e to the 1/2 t plus c2 e to the 3/2 t. Okay, so that's the general solutions where c1 and c2 are arbitrary constants. Now, to find the particular solutions, that is the specific value of c1 and c2, you need to write down the, you need to utilize the initial conditions. So given y of 0 equal to 2 and y prime of 0 equal to 1/2, we get that. So y of 0 is c1 times e to the 0 plus c2 times e to the 0, or c1 plus c2 equal to 2. So that's one equation. The second equation is coming from the second initial conditions, y prime of 0 equal to 1/2. So y prime of t is equal to 1/2 c1 times e to the 1/2 t plus 3/2 times c2 times e to the 3/2 t. Okay. So y prime of 0 give you 1/2 c1 times e to the 0 plus 3/2 c2 times e to the 0, or 1/2 c1 plus 3/2 c2 equal to 1/2. Okay, so you have two equations here. The first equation, c1 plus c2 equal to 2. The second equation is 1/2 c1 plus 3/2 c2 equal to 1/2. So you get a system of linear equations with two equations and two unknowns. Right, so the system is c1 plus c2 equal to 2, and 1/2 c1 plus 3/2 c2 equal to 1/2. You can simplify the second equations by multiplying 2 across, and you get c1 plus c2 equal to 2, or c1 plus 3c2 equal to 1. Again, you can use eliminations method or substitution method to get the solutions of c1 and c2. So in the last lecture, in the last example, I used elimination method. In this example, I mean, you can use elimination method as well, but I want to try substitution method. So that is, I'm going to set c1 equal to something in terms of c2. Okay, so from here, I get c1 equal to 2 minus c2. Then I can substitute c1 into the second equations. So from here, you get c1 to be 2 minus c2 plus 3c2 equal to 1, or 2 plus 2c2 equal to 1, or 2c2 equal to -1, which implies that c2 is equal to -1/2. When you know the value of c2, you can find the value of c1. So c2 is equal to -1/2, implies that c1 equal to 2 minus -1/2, or 2 plus 1/2 equal to 5/2. Okay, so c1 equal to 5/2, and c2 is equal to -1/2. Therefore, you get the particular solution as. So the particular solution is y of t equal to 5/2 times e to the 1/2 t minus c2, so plus c2, that is minus minus 1/2 times e to the 3/2 t. So that's it for this lecture. It's a shorter lecture because the focus is on the method of characteristic, but only for distinct roots. Okay, we will tackle the case of complex root and of the repeated root in other lectures. So in this case, what we did is that we look at the method of characteristic. This is the first solution method to solve the second order differential equations. But more specifically, the focus is on the homogeneous linear second order differential equation with constant coefficients, or the equation of the form a times y double prime plus b times y prime plus c times y equals to 0. And to get the solutions, we kind of make a trial solution. We use a trial solutions of the form y equal to e to the rt, and then substitute that into the differential equations to arrive as a characteristic equation or auxiliary equations or the quadratic equations. And you use the quadratic formula or some factor of the quadratic formula to find the factor of quadratic equations to find the root of the quadratic equations, right? It depends on the value of b squared minus 4ac. When that is positive, you have two distinct roots. When that is equal to 0, you have a repeated root. And when that is less than 0, you have a complex root. In this lecture, we did some example related to the case of two distinct roots. We find the general solutions, we find the particular solutions based on the initial conditions. And in finding the general solutions, you first arrive at solutions y1 and y2. Then you check that the Wronskian of the two solutions is different from 0. Then you can write the general solutions. Then you use the initial conditions to find the specific value for C1 and C2. Then you arrive at particular solutions. So that's it for me for lecture 9. I'm going to move on to lecture 10.